So the next very interesting idea in whole of probability and statistics is called probability distributions. Now, before we go into the exact distributions that we will study, let's understand the concept here. So what happened was when mathematicians and statisticians, when stats guys and math guys actually, when they observed natural phenomenon, right? When they observed natural phenomenon, right? Lot of things that happen in nature or in science, right? So when they observed lot of natural phenomenon, right, they realized that there are some things which are very similar. Let me give you an example, okay, to explain what I mean by this. For example, imagine if I'm tossing a coin, right? Take the example of a coin toss. What happens in a coin toss? Coin toss, if you think intuitively, has two outcomes, right? Has two outcomes. It has either a tails or a head. It has two outcomes. Now, instead of calling them heads and tails, if I call this as 0 and if I give this a number 1, I'm just giving two numerical values associated with this. So imagine if I have a random variable x that takes 0 for a coin toss. It takes 0 if the coin toss results in a tails, and it takes a value of 1 if the coin toss results in a value of head. So if you think about it, this is a discrete random variable, right? First, let's start with this. This is a discrete random variable, right? And x can take only two values, 0 and 1, right? And equally importantly, the probability of x taking the value 1 in this case, in the case of a coin toss, is half. Let's call this as small p, right? Now, probability that x equals to 0 is nothing but 1 minus half, right? Which means the probability of it taking tails is nothing but 1 minus the probability it takes heads. Now, this is also equal to half, and this is given a value called as q typically, right? Let's look at this example, right? Similarly, there are many examples. There are many examples in nature. I'll give you another example, right? For example, if you want to take this example, okay. So if I want to create a random variable x which says, will it rain tomorrow? Okay, will it rain tomorrow? Right? Will it rain tomorrow? I'm not worried about what is the amount of rain. I'm only caring whether it will rain tomorrow or not. This also can take two values. It can take a true or a false, right? Yes, it will rain tomorrow. No, it will not rain tomorrow. So if I give this value 1 and if they give this value 0, if you think about it, just like your coin toss, this random variable x also can take two outcomes, and we're just calling these outcomes as 1 and 0. Now, if you think about it, the probability that x equals to 1, the probability to rain tomorrow is going to be very small. Given any day of the year, if you think about it, there might be maybe 15% chance that it will rain tomorrow. On the other hand, there will be so what is probability? So if I call this as p, what is probability that it will not rain tomorrow, right? What would it be? It would be 1 minus p, which is nothing but 1.85, and we call this q. If you think about it, in both these cases, again, both are very real world phenomenon, right? In both these cases, this experiment that I am conducting, right, has two outcomes, and the probability of one outcome is p, and the probability of the other outcome, we are calling it q, and q is nothing but 1 minus p. But there is one distinction here. In the case of coin toss, the p and q, both of them are equal to half. In the case of will it rain tomorrow, right, p equals to 0.15 and q equals to 0.85. See, the p values are changing, but the concept itself, they both look very similar, right? If you think about it, this random variable and this random variable look very similar, except for the fact that the probability that this will take a value of 1. So this is typically called as success probability, right? So because we have only two values, right? This is called success probability. This is called failure probability, typically. General names given to it, right? So the success probability and failure probability values are different here, but the conceptually, at the level that these two random variables actually take only two outputs, and the probability of one output, if I call it p, the probability of the other output is 1 minus p, which I can also call as q. Right? If you think about it, they both are very similar at an intuitive level. Similarly, let me construct one more example for you, right? So let me construct one more example for you. Imagine if I have a random variable x. Okay, let's take an example from e-commerce. Okay, will a given customer purchase, will a given customer purchase a product, Right? For example, imagine if you're a statistician or a computer science or a computer scientist or a machine learning scientist, right, at an e-commerce company like Amazon, Flipkart, etc. This is very important, right? Will a customer purchase a product or not? There are two outcomes here, yes and no, right? If it is yes, I'll give it a value of 1. If it is no, I'll give it a value of 0. So if you think about it, this random variable also takes two values. And the probability that x equals to 1, which means the customer actually purchases a product, maybe only small, right? Because not every customer purchases every product. Right? There may be a 5% chance that a customer purchases a specific product. While on the other hand, there is a 95% chance, if this is 5%, because there are only two possible outcomes here, this has to be 0.95. Right? If this is P, this is Q. Look at this. This is another example from a completely different domain of e-commerce and retail. Right? Completely different context. This is in weather. This is in weather. This is some simple toy example. Now, in all these cases, what statisticians and mathematicians have observed is, in all these natural phenomena, there is a pattern. So they said, can we now understand this pattern? Can we now understand the pattern? Can we now understand the pattern and study the pattern itself? What is a pattern here? Look at this. And these patterns are called as probability distributions. Now, what is the pattern between these three examples? Again, I can give you one more example, right? I can give you one more example just so that the concept is more solidified for you. The gender of a newborn baby, right? The gender of a newborn baby, right? The gender of a newborn, right? It can either be male or female, right? Let's assume male equals to 0 and female equals to 1. So my random variable x now also takes two possibilities, and the probability that a newborn baby is female is approximately 50%, which is equal to your p. Similarly, the probability that the newborn is a male is also roughly 50%, and we call this q. Look at this. This is a completely different domain of medicine, right? Whether newborn is a male or a female. So if you look at all these examples, they all have the underlying pattern. This pattern here, let me write down the pattern, right? The underlying pattern is this, that this random variable x takes two values, right? So let's call this, see, it can take two different values, male, female here, yes, no here, true, false here, tail and heads here, but just give some general numbers, 0 and 1, okay? And the probability that x equals to 1, let's give it a special name called as P, or success probability. This is also called as success probability, right? See, since I have two outcomes, two distinct outcomes, I can call them 0 and 1, right? And now the probability that x equals to 0 will be equals to 1 minus P. Obviously, because there are only two outcomes, they both have to sum to 1. These two probabilities have to sum to 1. And this is often written as Q, and this is called as a failure probability. Now, what is important here is, for each of these instances, in each of these instances, the p-value is different. Here the p-value is 0.5, here the p-value is 0.05, here the p-value is 0.15, here the p-value is 0.5. The p-value is different, but the underlying phenomenon is the same. Which means, if somebody tells me this, if somebody gives me this idea, if somebody says this random variable x, right, has only two outcomes, they have to give me two realities, right? That it has two outcomes, two distinct outcomes. This is one thing that they have to tell me. Second thing that they have to tell me, that the probability of one outcome, let's call that outcome as 1, is equal to P. If you give me P, I can compute Q. Q is nothing but 1 minus P, right? So if they give me these two things, right, then all of these natural phenomena are very similar. So what statisticians and mathematicians have done here is they have tried to understand the underlying pattern and study them. These underlying patterns are nothing but probability distributions, right? Suppose now, instead of studying coin tosses, instead of studying whether it will rain tomorrow or not, instead of studying whether a customer will purchase a product, instead of studying the gender, if I study a distribution, if I study a random variable which has two outcomes, and the probability of success is P, and the probability of failure is Q, which is nothing but 1 minus P. If I study this theoretical model, look at this. This is a theoretical model, right? This is a theoretical model. Now, if I study this model, tomorrow if you give me another example, right? Will a person will a person have an accident tomorrow? Will a person have an accident tomorrow? A car accident or something like that, right? Very, very low probability. Here the probability will be 0.0001 maybe, right? Very low probability that somebody has a car accident, right? But this is also a very similar problem where there are only two outcomes, yes and no. So yes if it is 1, no is 0. So now if I study this theoretical model, right, I can also, and if I can find some interesting results on this theoretical model, I can apply those results to any of these 5 problems, any of these 5 real world problems. And this theoretical model is what a probability distribution is. Right? This theoretical model that mathematicians and statisticians have made up to understand the properties of this of a random variable which has these 2 requirements. If you can study them mathematically and very rigorously, you can apply the ideas and the outcomes and the properties you learn from this to other problems. We'll see what. Okay. So again, this is such a random variable. So the first distribution that we will learn of is called as Bernoulli distribution. Right? It is called as Bernoulli distribution. Right? After the mathematician whose name is Bernoulli himself. Right? Again, Bernoulli is a mathematician and a physicist. Okay, sounds good. So now let's come here. So this distribution, so a random variable x is said to be, so this basically means x follows a Bernoulli distribution. X follows a Bernoulli. The moment you say Bernoulli distribution, I know. The moment you say Bernoulli distribution, I know that x can take only 2 values. And Bernoulli distribution, when I say Bernoulli distribution, it is automatically clear that x only takes 2 values. Along with for Bernoulli distribution, I need one more information, right? What is the probability P? What is P? P is nothing but probability x equals to 1. Look at this. If you give me a random variable wherein you tell me that it has exactly 2 outcomes, and if you give me the value of P, I can understand this random variable. All these 5 random variables I can understand. If you just tell me these 2 without telling me the real world context. This is my mathematical model, right? Similarly here, in the case of a Bernoulli distribution, if you just tell me that x is a random variable, which follows, so this basically means x is a random variable which follows Bernoulli distribution. The moment you say Bernoulli, it's very clear for me that it has only 2 outcomes. And if you give me a value of P, if you give me the probability of success, then I can say everything about this random variable. Okay, let's see, what do I mean by everything? So again, here P is called the parameter of the distribution. P is called the parameter of the distribution. Okay, so P is called the parameter of the distribution, right? Now let me answer some interesting things, right? So now, x is a discrete random variable. Let's understand some basics here, right? X is obviously a discrete random variable because it has only 2 outputs, right? It's a discrete random variable. Now, if you tell me, without telling me whether it is the accident data, whether it is the gender of the newborn, whether it is a customer, without telling me anything, if you just tell me that x is a Bernoulli random variable, and if you give me a value of P, can I now plot its PMF? Because it's a discrete random variable, it will have a PMF, right? Very simple, because it has only 2 possibilities, right? 0 and 1. No other possibility exists. Now, what will the PMF be? This PMF will look like this. This height will be equal to P. This height will be equal to 1 minus P, right? And this height will be equal to P, right? So if you just tell me that x is a random variable without giving me any real world context, you're just giving me a mathematical model here. You're saying x is a Bernoulli distributed random variable. Again, we often say x is a Bernoulli random variable, which means x follows Bernoulli distribution with some P. And if you give me this parameter, you have to give me 2 facts. One is the type of distribution. The second one is the parameters of the distribution. If you give me both of them, I can plot its PMF. If you give me P equals to, let's say 0.3, right? Then I can say P equals to 0.3, 1 minus P is 0.7, which means this has to be taller, this has to be shorter. Now we have gotten PMF. Now can I also get CDF now? Right? Look at this, PMF, CDF. I can answer lots of questions if you tell me PMF and CDF, right? We have seen some questions that we can answer. If you give me PMF, if you give me this chart, I can answer lots of interesting questions for you. Similarly, how will the CDF look like? Look at this. This is my 0. This is my 1. So what is the probability? So what is the probability that x equals to 0? So it is exactly equal to 1 minus P, right? What is the probability that x is less than equal to 1? Because it can only take 2 values now. It can only take 2 values. This will sum to 1. This will sum to 1. So what is the probability that x is less than equal to 2? So there will be 2 here, right? What is the probability that x is less than equal to 2? It is same as probability that x is less than equal to 1. Because x does not take any other value apart from 0 and 1. So this will look like this for you. This is how your CDF will look like. So what is the probability that x is less than or equal to 0.5? It is same as probability that x is less than or equal to 0, because x cannot take any value between 0 and 1. Right? Again, a very interesting thing. Now the next thing is mean. What is the mean of your random variable x? Or what is mean of x? Mean of x is nothing but expected value of x, which we often write as mu. What is it? What is the definition of expected value of x? We have seen this. Expected value of x is integration over all possible values of x into px. Now what all values can x take? X can take 0 and 1. So 0 into probability of 0. What is probability of 0? Q plus 1 into probability of 1. What is probability of 1? P. Because that's a parameter that is given to me, right? So let me write it as small p. This is equal to p. So which means if you give me a Bernoulli distributed random variable, its mean is going to be equal to p. Now look at this. A person, so the moment you tell me that this is a Bernoulli random variable, the moment you tell me that it's a Bernoulli random variable, because it has only two outcomes with a value of p, which is this. Then if you ask me what is the mean value of x, right? I can easily say this mean is nothing but p, because it's a Bernoulli random variable. I've already studied this model. Look at this. Here are all the properties. Okay, I know if you just tell me that x is a Bernoulli random variable, I can draw its PMF, I can draw its CDF, I can compute its mean. Similarly, I can even compute its variance. Look at this. I can also compute its variance. What is variance of x? We have seen variance of x as expected value of x square minus mu square. We've already seen this, right? And what is mu? Mu is nothing but p. Mean is nothing but p. So we know that this is equal to p square. So what is expected value of x square? It is summation over all x square px minus p square, right? Because mu equals to p. Now what is this? Let's look at this, right? So 0 square is 0 into q, because probability of 0 equals to q. And remember that q is nothing but 1 minus p here. Let's not forget that fact, right? Plus 1 square is 1, probability of x is p minus p square, right? So what is this? This is 0, p minus p square. And how can I rewrite this? I can rewrite this as p into 1 minus p. And what is 1 minus p? 1 minus p is q. So this I can write it as pq. So now, if you just ask me, okay, so if you tell me that this real world phenomenon follows a Bernoulli random variable, right, follows a Bernoulli distribution with some value of p, I can tell you its mean, I can tell you its variance, because for a general random variable which follows Bernoulli distribution with some value of p, right, for some value of p, I have already computed the theoretical model. All the theory says if you have a random variable x which is Bernoulli distributed with a p, the mean of it is p, the variance of it is pq. Similarly, look at this problem, right? Look at this problem. Will a customer purchase a product? What is its mean? The mean of this random variable x, equals to 0.05. Right? What is the variance of x? Again, without even thinking about it, because I know this is a Bernoulli random variable whose p is 0.05. I can say this is, if you just give me p value, 1 minus p value. Look at this. I'm not computing anything special to this. And this is the innovation that mathematicians and statisticians have done. They've looked at lots of natural phenomena which occur over and over again, and they've built a mathematical model for it. And these results like PMF, CDF, mean, variance, these are all properties of this distribution, right? And now if somebody tells me, given some real world phenomenon, right, if it has two outcomes and the probability of success is p, right, that's it, I'm done. I can tell you what the mean is, I can tell you what the variance is and everything else, right? This is a very, very interesting innovation in the whole study of probability itself, because these are very, very powerful models. Again, we'll show you some, as we progress through some more examples, I'll show you tons of examples where these distributions are super duper useful. Okay, sounds good. So another important thing here is, suppose you are given some data, right? Suppose you are given some raw data, and you have to estimate p, right? Suppose you have to estimate the value of p. So you're given some raw data. For example, let's assume, okay, so let's take some simple examples wherein, okay, so let's assume some raw data, right? It could be, let's say, okay, it could be something like, Okay, let's take this example. Okay, let's take any of these examples. Any of these examples will do. Okay, will a customer purchase a product? Okay, let's take this example, right? Suppose I work at an e-commerce company. Customer 1, has he purchased or not? It's 1 or 0, right? So 0. Customer 2, has he purchased or not? 0. Customer 3, has he purchased or not? 0. Customer 4, has he purchased or not? 1. Customer 5, not purchased. So on and so forth. Customer 1 million, right? I have this raw data, right? So I can take this data of almost 1 million customers. Now I know whether a customer purchases or not is a Bernoulli random variable, right? I know this random variable X, which measures whether a customer purchases or not. I know this is Bernoulli because there are only 2 outcomes. Now I have to estimate what is the value of P. How do I estimate the value of P? Given some raw data like this, given some data for 1 million customers, how do I estimate my P? Or what should be the appropriate value of P, right? So my estimate of P, which is often written as P hat. So because P is a parameter, right? Look at this. P is a parameter, right? I know because it has only 2 outcomes. I know that it is Bernoulli distributed. Very easy to know that. Next is I have to now estimate the parameter of the distribution so that I can make some interesting conclusions from this. For example, what is P hat? P hat is nothing but number of ones by number of zeros plus number of ones in your raw data. Now let's assume this turns out to be 0.001. Let's assume my P hat turns out to be 0.001, which means for this natural phenomenon, my P is nothing but 0.001, which means I can now compute the mean of this, right? Now I can compute the mean of this and say mean of this equals to 0.001. I can also compute the variance of this. I can plot it CDF and PDF and all of that stuff. The moment I have PDF and CDF, I can start answering questions like, what is the probability that X is less than equal to 1? Or similarly, what is the probability that X is less than equal to 2? I can start answering all these important and interesting questions, right? So this is called the estimation of the parameters, okay? Because P is a parameter of the distribution. Here we're estimating the parameters of the distribution, right? So Bernoulli is one of the simplest and one of the most widely used distributions in the real world. Now, just like Bernoulli, there is a very related distribution called as binomial distribution. Okay, now I hope it is very, very important for you to understand why we are studying distributions. Not just the properties of the distribution and the mathematical algebra. You have to understand why statisticians came up with these concepts of probability distributions and why they are useful in the real world. I've seen a lot of students who can prove things for me without understanding why the heck we need distributions in the first place, right? So the next distribution is called as a binomial distribution. Okay, so binomial, so without going again into why we need a distribution, I'll go into examples of binomial distributions, right? So let's look at, again, this is a completely different type of phenomenon. Like for example, imagine I have imagine if I have n patients. Imagine I'm testing some medicine or drug, right? So this is in drug testing or medicine testing. Suppose I'm designing a new medicine as a pharma company. So when I'm designing a new medicine, completely new drug or new medicine, suppose I have a pool of n patients on whom I'm testing this drug, right? Suppose I have a pool of n patients. Now, so I want to study what is the probability. I want to study the probability that k patients will benefit from this drug, right? Will benefit from this medicine or drug, right? Will benefit from this medicine. K out of n, of course. K out of n patients. So I take n patients. Suppose I take a set of n patients. Let's say n equals to 100. Right? Now, given this set of 100 patients, I want to estimate how many patients will benefit from this drug, or how many patients' condition will be cured because of this drug. Right? So this is one example. So in this case, if you think carefully, again, this is a real world example in medicine and pharmacy. Right? This is actually a real world example. Right? This is not some cooked up coin toss type of toy example. So here, if you notice, suppose if I have patient 1, patient 2, so on and so forth, patient n. The outcome of the medicine or the drug on patient 1 is independent of the outcome because of this drug on patient 2. Look at this, these n outcomes, right? Because for each patient, there are 2 outcomes. I'm sorry. For each patient, there are 2 outcomes, 0 or 1. Let's say 0 means that the drug did not help the patient. 1 means that it helped the patient. Similarly, for this patient also, there are 2 possible outcomes, 0 and 1. so on and so forth. For every patient, there is 0 and 1 possibility. Now, see, look at this. So which means whether this drug cures a patient 1 behaves more like a Bernoulli random variable. Look at this. Because if I think of, see, instead of worrying about the probability that K patients will benefit, if I say will patient 1 benefit because of this drug, there are only 2 outcomes, 0 and 1, right? Right? And let's assume there's a probability. Let's assume with 90% probability, with P equals to 90%, right? P1 will benefit because of this. So will a given patient benefit from it is a Bernoulli random variable, right? So say Bernoulli random variable basically is, will a given patient benefit? Will a patient benefit, right? Is a Bernoulli random variable. But the other way of asking is, out of n patients, will K patients benefit? Will K of them benefit? This does not have 2 outcomes, right? Again, look at this. If you think about it, out of n patients, how many will benefit? The other way to ask is, instead of asking will K benefit, out of n patients, how many will benefit? How many will benefit? Right? This is another way of asking. Again, this is very, very important in medicine, right? Because imagine there are 1 million people who are suffering from some disease, and you designed a new medicine, right? Now, your n is equals to 1 million. Now, you want to say of these 1 million, almost 99% of them, or some number of them will surely benefit because of this medicine, right? Very important, right? If you think about it. So the random variable which measures out of n patients, how many will benefit, this random variable is called as a binomial random variable, right? This random variable is called a binomial random variable, right? Of n patients, how many will benefit? And look at this, a binomial variable internally has a Bernoulli random variable when you look at it from the perspective of each patient, right? So let's also understand this from a slightly different context, right? So let's try to understand it from a slightly more toy example. This is a real world example. Let's also understand it from a simpler toy example. Suppose if I toss n coins. Okay, what is the probability that I get K heads? What is the probability that I get K heads in n tosses? And here, there are a couple of important things. Number one, these K tosses are independent. These n tosses. There are a couple of important factors here. These n tosses are independent of each other. Right? Second, the probability of a tail or a probability of a head or probability of 1, right? Probability that if I take a Bernoulli random variable for each coin toss, this is, let's say, equal to 0.5. For each of the n tosses, for each of the n repetitions, for each of the n trials, right? For each of the n trials, this probability of success for each of the n trials. So let me write it. For each of the n trials, the probability of success, right, which in case is nothing but probability of x equals to 1, remains the same. This is very, very important. It remains the same. The probability does not change. Number 2. Number 3, in each trial, right, you can consider each trail, you can consider it as a Bernoulli random variable. Each trial you can consider a Bernoulli random variable with some value p. Now, if a real world phenomenon satisfies these 3 things, which means the n trials are independent, n trials or tosses are independent, the probability of success for each of the n trials remains the same, and in each trial, right, each trial follows a Bernoulli Bernoulli distribution. Look at this, even here, right? Look at this. Me giving a drug to each of these patients, and checking out if they're actually successful or not is a Bernoulli random variable. And because I've designed a general purpose drug, the probability that patient 1 will be cured or will benefit from this drug is same as the probability that patient 2 will benefit from this drug. And me giving a drug to patient 1, me giving a drug to patient 2, so on and so forth. These n trials are independent. So it satisfies the n trials independent case. The probability of success, which means the probability that the patient will benefit from it, is the same across all patients. And me giving a drug to each of these patients is a Bernoulli random variable to start with, right? So if it satisfies these 3 conditions, we defined the statisticians, we as in the statisticians built a new technology or a new distribution called as binomial distribution. Again, we'll study properties of binomial distribution, right? So binomial distribution has 2 parameters, P and N. Now what is P here? P is nothing but your probability of success in each trial. Right? In each trial. So what is N? N is the number of trials. Right? So again, we can easily compute this. Look at this. Look at this simple toy example of coin toss, right? Suppose the probability of getting one head is P. Okay, so probability of one head. Probability of a head. Okay, we'll derive the math here and we'll then extend the concepts here. The probability of a head in a given coin is, let's say, P. Right? Now look at this. Now, probability of K heads in n tosses. We can easily compute this, right? In n tosses, I can choose any K heads. So I can choose K heads out of n tosses. Now, if I choose K head, if I choose the specific set of coins, of the n coins, I have to choose K coins in which I want to get a head. I can do that in NCK ways. Now, given a head, right, given these K coins on which I want heads, what is the probability that all of them will get a head? P power K. And when all of them get heads, rest of the n minus K points should not get a head, right? So this is Q power n minus 1, because Q is nothing but probability of tails, right? Of course, which is equal to 1 minus P. Again, very, very simple combinatorial derivation. What is the probability that I get K heads out of n tosses, which is same as asking in a given Bernoulli random variable, if I have n trials in one experiment has n repetitions of the same thing. If I have n trials, of these n trials, how many times will I get K successes, right? Same question. And the result is the same. From n coins, I can choose K coins in n choose K ways. For these K coins, I have to get a head. And for the n minus K coins, I have to get a tails. So this is your probability. So your random variable X, so let's define it. Your random variable X can take 0, 1, 2, up to n values. Right? Your random variable X can take any of these n plus 1 values, right? And now the probability that X equals to K is nothing but, it's also written as Pk, is nothing but n choose K, P power K, 1 minus P power n minus K. So this is my, if you think about it, this is my probability mass function. Okay? This is my probability mass function. We'll go to the plot of PMF in a little while, right? So what about the CDF? CDF basically measures probability X less than equal to K. This is nothing but summation I equals to 0 to K, n choose I, P power I, 1 minus P power n minus I. Right? Simple definition of CDF. Now, all this is cool. Now there is, okay, we'll go to a real world example. I'll actually shed this to you in a real world example. Remember here, there is one very common misconception here, which is, okay, I'll tell you that with an example in a little while. Okay, first let's finish the math part of it, right? So X is said to be Bernoulli. Again, Bernoulli random variable has 2 parameters, N and P, right? N is the number of trials in an experiment. Look at this. In each experiment, we have n repetitions of the same binomial random variable. So you can actually write, if you think about it carefully, you can write your X as summation of, you can think of your random variable X as x1 plus x2 plus x3, so on, xn. Now each of these, any of these xi's is a Bernoulli random variable. Look at this. If each, you can think of it this way, right? Because look at this. When I say what is the probability that I get K successes? What does that mean? It is equal to saying what is the probability that the sum of these random variables equals to K. Because if I get a success here, I'll get a value of 1. If I get a success here, I'll get a value of 1. So probability that x equals to k is same as probability of summation over xi's equals to k. Right? Because if you think, because remember, a Bernoulli random variable, sorry, a binomial random variable, again, these are very confusing because they both start with B. I get confused a lot sometimes. Then I take a step back. I think, okay, something that is named after a mathematician has only 2 outcomes. Something that is done after a binomial expansion is a sum of Bernoulli random variables, right? Again, this is a common confusion that I had ever since my undergrad days. Sounds good. So now let's see. A Bernoulli random variable is a sum of binomial random variables, right? You can think of it this way, right? If you think mathematically, because each of this can take a value of 0, 1. This can take a value of 0, 1. This can take a value of 0, 1, so on and so forth. So what is the probability that x equals to k? Nothing but I get k once here, right? That's what it is, right? The summation I equals to 0 to n, right? I equals to 1 to n because I have n trials here. I equals to 1 to n is equal to k, right? Now with this you can prove a lot of it. See, this is a very, very important mathematical step. This is a super duper important mathematical step because given this, I can compute the mean of a Bernoulli random variable, or a mean of a binomial random variable, right? We're only worried about binomial random variables now, right? So I can compute the mean of a binomial random variable as expected value of x. And what is expected value of x? Expected value of x is nothing but expected value of x1, x2, so on and so forth, xn. Remember that each of these xi's are Bernoulli random variables. So this is nothing but, again, we've seen this formula, right? Expectation of x plus y is expectation of x1 plus expectation of x2. We have seen this property in one of the previous videos, right? Plus expectation of xn. Now what is, so this is nothing but mean of the first random variable. Mean of the first random variable is p. Mean of the second random variable is p. Similarly, n times. So this is equal to n into p. The simplest way to derive it, right? Of course, you can also derive it differently. You can say mean equals to expected value of x. See, this is a simpler way of deriving it. There is another mathematical way of deriving it, right? So this is nothing but, if you think about it, what is this? This is nothing but summation k equals to 0 to n, right? K into p x equals to k. Now what is this? This is the definition, right, of expectation of x. K equals to 0 to n, k into, what is p x equals to k? Nothing but n choose k, p power k, 1 minus p power n minus k. Now if you solve this whole thing, if you simplify this whole thing, you will get np. Again, you can take this up as an exercise. Simple algebra, if you go through some simple algebra, you can show that this is equal to np. But this way of computing the mean is a much more elegant way because it's literally 2 steps instead of simplifying this complex looking expression. Now what about variance? What about variance of x, where x is a binomial random variable, right? What is the variance of x? Now look at this. Variance of x is nothing but variance of x1 plus x2 plus x3, so on and so forth, xn. Because x is nothing but x1, x2, x3, xn. Now remember that x1, x2, x3, so on and so forth, xn are independent random variables. They're not dependent at all. Because my outcome, look at this, my outcome in the first trial is completely independent of the outcome in the second trial. Or in other words, my outcome of the drug on patient 1 is completely independent of the outcome of the outcome on patient 2 and so on and so forth. That's what we even said here, right? For each of the n trials, the probability remains the same and the n trials or tosses are independent of one another. We said this as a requirement for Bernoulli random variable, right? So because x1, x2, x3 are independent, the variance of this can be written as variance of x1 plus variance of x2, so on and so forth, plus variance of xn. This is a very important property about variance. Again, we can also prove this by writing the formula of variance. Again, variance of sum of random variables equal to the sum of variances of these random variables if they are independent. Again, this is fairly simple to prove from expectation concepts, right? Now, what is variance of x1? Variance of x1 is p into q. Variance of x2 is also p into q. So on and so forth n times. Now, what will this be? So, this will be equal to npq, or this can also be written as np1 minus p, right? Look at this. Look at how I am able to compute. See, the moment you tell me that X is a Bernoulli random variable with these two parameters, then I'm simply able to tell you what the mean is, what the variance is. Now, the next very important topic here is given some real world data. Okay, before going to the real world data, let me give you another very real world example where Bernoulli random variables are extremely widely used. This is in manufacturing, right? This is in manufacturing, right? Suppose I'm manufacturing some light bulbs. Again, we have seen this example earlier, right? Suppose let's assume I'm manufacturing some light bulbs, and every pack that I sell, let's assume has 100 bulbs, right? Every pack that I sell has 100 bulbs. Now the probability that a bulb is faulty, see, this type of concept is true for bulbs, for cars, for anything, for a pen, for a laptop, for anything you can, for a mobile phone, right? Probability that a bulb is faulty is, let's say, 0.01. 1% of bulbs are faulty, let's say. Now the question here is this. Now I've packed 100 bulbs in one packet. Again, there is one more shipment of 100 bulbs. Suppose I send each of these to my distributors who distribute them to other places, right? So there are these 100 packets. Now I know that the probability of the bulb being faulty is 0.01. Let's call it P. Now the question I want to ask is this: probability that any of these packets, suppose if I want to compute probability that K out of these 100 bulbs in a packet, K out of 100 bulbs in a pack are faulty, right? K of them are faulty. It's a very important question, right? If I'm a distributor who is buying these and then unpacking them and selling them to someone else, right? I have to know how many of them are likely to be faulty, right? Isn't it? So if I want to know what is the probability that 2 of them are faulty, this is a real world problem. You can think of it as a Bernoulli random variable. With P equals to 0.01 and N equals to 100. Why is N equals to 100? Because in each pack I'm putting in 100 bulbs, and each of these bulbs can be faulty by this way. So what is the probability that K out of 100 bulbs are faulty? It is nothing but N choose K, or 100 choose K. N here is nothing but 100 choose K, P power K, and Q power N minus K. Now using this, I can compute the probability that 2 bulbs are faulty or 5 bulbs are faulty in a pack. Look at this. I'm only worried about a pack now, right? So given a pack of 100 bulbs, which is equal to 100 trials, because each bulb, whether it works or not, I can think of it as a binomial, as a Bernoulli random variable. And the sum of all the outcomes here, I can think of it as a binomial random variable, right? Again, this is very, very important. Now comes the problem of estimation. So let's go into the problem of estimation now. Okay, how do you estimate, given some real world data, how do you estimate P? N, of course, you have to be given. For example, let's take the example of the bulbs itself, right? So the bulb manufacturer says in each packet, I give 100 bulbs. Very good. And it says in packet 1 that I shipped, 2 bulbs were found to be faulty. In packet 2 that I sent, 0 bulbs have found to be faulty. In packet 3, I found 3 bulbs to be faulty. Packet 4, we have seen 1 bulb to be faulty. So on and so forth. Some packet 10,000. We have seen only 2 bulbs to be faulty. I'm given some real data like this. Again, this is each pack containing 100. So this is my real world data. Now, given this real world data, I know that this follows Bernoulli. I also know the value of N because the manufacturer told me that in each pack I'm putting in 100 bulbs. But what is the value of P now? If I can estimate the value of P, right, I'm done. That's the only other parameter that is not obviously visible to me. The manufacturer tells me that N equals to 100. But what about P? How do I compute P? Again, P is very simple to compute. P is summation over, let's say this value is x1, this value is x2, this value is x3, so on and so forth, xm. Okay, let's say these are xm values. So this is equal to I equals to 1 to n, xi by x equals to I to m, because I have m packets here, right? N into m, right? N is 100 now. So I can just compute this and this will give me the estimate. It's an estimate. Remember that this is an estimate. This is an estimate. Again, we often write estimates with a hat in probability and statistics to clearly say that this is not the actual value of P, but this is the estimated value of P from some raw data, right? Again, for each distribution, what we will do is this. We will understand where the distribution arises in nature. We'll give you a couple of real world examples for each distribution. We'll also understand the properties on when this distribution is going to be satisfied. And we'll also understand some properties like what is the mean of the distribution, what are the parameters of the distribution, what is the variance of the distribution, and how to estimate the parameters of the distribution. Again, I forgot to show you this, right? I mentioned this to you a while ago, right? We'll see how PMF and CMF plots look like. So let's go to Wikipedia now. Okay, beautiful plots. Again, I'm on the page called binomial distribution. If you just Google search for binomial distribution Wikipedia, you'll get this page. Now look at this red line here. This red line is the PMF. This red line here is the PMF of a Bernoulli random variable when p equals to 0.5 and n equals to 40. Look at how it looks like. It looks like it has dot 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 dot. See, this is not a continuous curve, right? It looks like this. Again, we'll come back to curves like this when we study something called as normal distribution a little later. Then we'll connect these concepts also. Look at this green line here. This green line is your p equals to 0.7 and n equals to 20. This blue line here is p equals to half and n equals to 20. So if you actually plot the PMFs, this is how they look like. Similarly, the CDFs will look like this S-shaped curves. They're not continuous. Look at this. So they look like bells. They look like a bell, but they're not continuous. Look at this. They look like a bell, right? They look like a bell, but they're not continuous. They're discrete. Similarly, here also it looks like a shape. It looks like an S. If you look at this, this looks like the integration sign or an S, but it's not continuous. Remember this. Okay. Keep this in your mind because we will revisit this concept in one of the future distributions. A very, very popular distribution called normal distribution, where the plots will look like this, but they'll be continuous. Right? Again, these plots are super duper important because they give you a sense of, because if somebody gives me this plot, okay, let's look at it the other way around, right? So if somebody gives me this plot and tells me what is this distribution, because I know the form of the plot, if somebody draws this line, if somebody draws this dots for me, I'll immediately understand that, okay, this looks like a Bernoulli random variable. I can immediately decipher that, right? So I hope you understood why we need random variables, why we need probability distributions on random variables, and two of the most popular distributions that we often encounter.